5.3, we'll solve exponential equations, solve logarithmic equations, and do a little change of base theorem. Change of base theorem is real simple. It's just the log of the argument divided by the log of the base. And it doesn't really make sense until we start to solve logarithmic equations. But notice this is log base 6, right? And if you just have your calculator right here, there's two buttons on your calculator. There's log, which is base 10, and natural log, which is base e. I don't have a log base 6 button on my calculator to figure out what log base 6 of 18 is. But with this rule, which I'll explain later once we go through how to solve a logarithmic equation, to figure this out, you just take the log of the argument divided by the log of the base, and when you do the logs, they're now in base 10. So who's the argument? Is it 6 or is it 18? So this is really log of 18 divided by log of 6. And then they want us to round it to 4 decimal places. And the hardest part about it is typing it in your calculator. You type in the log of 18, and like I said, what makes it hard is because your calculator automatically puts that parenthesis there for you. You need to close that parenthesis so you can then divide that by the log of 6 and round that to 4 decimal places. So that is about, let me switch, about 1.6131. Cool. Don't forget the approximate symbol. Cool. Log base 8 of the square root of 2. Well, that's going to be the log of the argument over the log of the base. So the log of the square root of 2. And now you got to close 2 sets of parentheses because they have you put the square root of 2 in there. Then you got to close the parentheses for the log. All right, you with me on that? Then divide it by the log of 8. And rounded to 4 decimal places, 0.1667. Cool. One more. Get that one done for me. Evaluate log base 7 of 40. When you're taking your test, I'd really like it if you wrote it out first, because if you just have something punched in and there's no work and I don't know what you punched in, I have to take away all the credit. So it's nice for you to show me that you took log of 40 divided by log of 7. Rounded to 4 decimal places. That's called the change of base theorem. And I'll explain it later once we have learned how to solve logarithmic equations. So now there's going to be 4 different scenarios. Scenario 1, you'll have some equations right here, and these are exponential equations. Notice there's no logs involved whatsoever. And the first thing you want to look for when you have exponential equations is, can you rewrite the bases the same? As you can see on number 1 here, this guy's base 2, and this guy is base 4. Is it possible to rewrite them with the same base? Is 4 like a power of 2? Yes or no? So we can rewrite this guy on the left. 4 really becomes 2 squared. Correct? Isn't that what 4 is as a power of 2? But all of that is still raised to that same exponent of x minus 1. And that will equal 2 to the x plus 5. And what's so great about that is now we can use our exponent rules. We've got a power to another power right here. What am I supposed to do with these exponents right here? Would I add them together or multiply them together? Multiply. So you really got 2 times x minus 1 as the whole quantity, though, right? Because this x minus 1, there's more than one term in there. So you got 2 to the 2x minus 2 equals 2 to the x plus 5. You have to distribute that 2 to each one of those guys. Rock and roll. Now that they're the same base, then if this is 2 to some power and it's got to equal to 2 to some other power, then the rule is the bases can just drop, and you're left with 2x minus 2 equals x plus 5. The exponents have to be equal to each other, and you solve for x. So subtract 1 over, 1x I should say. Cool. Then we should check our answers just to see if it worked. If I had this, my check would look like so. I have 4 to the 6, and I want to see if that equals 2 to the 7 plus 5 is 12. Punch them both in and see if they check. What's 4 to the 6? Big number, right? Then check in 2 to the 12th. Did I get the same thing? So, check. My solution was 7. Put it in a solution set. You cool with that? So, I'm not going to check nearly extensively as we did in Algebra 2, but we are going to check. We'll let our calculator do the work, and then if they don't check, we'll cross them out because they're extraneous answers. So, number 2, I want to try to write them as the same base. This is base 2. This is base 8. Is it possible to write them both as base 2? So 2 to the x equals, what's 8 changed into a power of 2? 2 to the third. But it's still got to be raised to the third. All I did was where there was an 8, I replaced that with 2 cubed. So over here, this is still 2 to the x. This would be 2 to the 6th or 2 to the 9th. What would that be? 2 to the 9th, power 2, power multiply. Since they're both base 2s, you can drop the bases, set the exponents equal to each other, x equals 9. Then you just want to check in that situation, right? So my check, you can just substitute 9 back in for x. Will 2 to the 9th equal the same thing as 8 to the 3rd? Did they check? So just put a check mark by it. Show me that you checked it, right? If you do it all in your calculator, all good in the neighborhood, but I just substituted 9 in for x. I typed in 2 to the 9th. I got 512. Then over here was 8 cubed. Typed that in. I got 512. Same thing. It checked. Solution was 9. Awesome. Rewrite those with the same base. Look at the smaller one. See if it's possible to rewrite with the same base. Yes, 9 is a power of 3. Then use your exponent rules. You must distribute that 2. So that's going to be 4x minus 2. Now that they're written as the same base, right, then you drop the bases and the exponents are equal to each other. Negative 2 equals negative 2x. X equals 1. My bad. 2x. X equals negative 1. So I will do a little check. When you get a negative exponent, it's easier to check algebraically than it is with a calculator. That would be 9 to the negative 2 minus 1. Isn't that negative 3? Right? See if that equals 3 to the negative 6. What you really do is the negative exponent, you now reciprocate the base. So that's 1/3 to the positive 6. And it'd just be much, much easier. And honestly, you don't even care about the 1s because 1 to the 3rd power will be 1. You care about 9 to the 3rd power, which is 729. See if that equals 1 to the 6th power is 1. 3 to the 6th power, also 729. It checked. If you punch it in with the negative exponents, you get nasty decimals. Not to say that you can't see that the two decimals are the same, but just the algebra behind it. Negative 1 was the solution. Try number 4 for yourself. Pause the video, get that done. See if you can rewrite them as the same base. Maybe they can both be base 4s. Maybe they can both be base 2s. Rewrite them as the same base. 64 can be rewritten as base 4. It's 4 cubed. Solve for n equals 2. Substitute back in. This turns out to be 4 cubed right here. And that definitely is 64, so it checks. And 2 is my solution. Awesome. Can these be rewritten as the same base? Yes. Base 5. What's 125 rewritten as base 5? 5 to what power? 5 to the 3rd. And that's still got to be raised to the x plus 2 power. Then you distribute the 3 to each one of those. So that's 5 to the 3x plus 6. I do want to see all this work on your test also, instead of going straight to what the exponents would equal. Then you drop the bases. exponents equal to each other. Then to check it, that would be 5 to the 15th, which is that nasty number. This would be 125 to the 5th. I got the same nasty number, so it's checked. What's that read? One weird problem on number 6, you got a fraction. That's where negative exponents come in. You can see that he is base 3. Just think about this guy over here as a 9 for a second. Could you rewrite 9 as base 3? 3 squared, correct? But how do you get that fraction in there? The exponent has to be negative. So this is still in base 3 over here. And this is really like 3 squared, but the exponent has to be negative, is why you get the fraction in that situation, because it reciprocated base. So since 9 is, let's say, 3 squared is 9, but you need it to be down in the denominator, that's why it's negative. Same basis, 2x minus 1 equals negative 2. Add 1, 2x equals negative 1. X equals negative 1/2. Uh-oh, let's check it. Negative 1/2 times 2 is negative 1 minus 1 more. You got 3 to the negative 2. Is 3 to the negative 2 really 1/9? Yes, it is, because 3 squared is 9, and you reciprocate it and get yourself 1/9. So check. Those are the simple ones, man. There were no logs involved, and the bases could be rewritten as the same thing. Over here, actually, I'll take that back. These are the simple ones. You have an equation. There are logs involved, but there is a log in every term, right? If there's a log in every term, realize here's one term right here. Here's another term right here. It is very much like we were just doing. If these are the same base, then shouldn't the exponents be equal to each other also? When it comes to logarithms, if they're both log base 4, right, you have the same base, then these arguments should be equal to each other. So you could get rid of the logs and say that 3x minus 1 equals 2x plus 3. Because there is a log in every term, you might make a note off to the side. I don't know if that has anything to do with it, but that's what this set of problems is all about. Every term has a log with it. Then you solve. And then the important thing is you must go back and check these, because there will be extraneous answers, because the argument, meaning the number next to your log, whatever base, this is the argument, this is the argument must be positive, meaning it cannot be a negative number, nor can it even be 0. So you got to check. If you put a 4 in for x right here, wouldn't you get 12 minus 1, which is 11? Isn't that good, right? It's not 0, and it's not negative. You check him, this would be 8 plus 3, which is 11. You did not get 0, you did not get a negative number, so this guy checks, right? All you do is go back to your argument and see if it turns to be a positive number, and that'll work. So 4 is my solution. Like if this was 11 and this was like 15 or something like that. If there's only log equals log, that won't happen, right? But it does happen to where you'll see some of these where we've got to condense them down together. Like here's a log, here's a different log plus another log. There'll be different things because this is 2 logs together, this is 1 log over here. You'll see that here. But when it's just log equals log, when you get down to that, you'll have to get the same argument back for them to be equal also. Good question. This one, sorry that I'm going to beat a dead horse. Does every term have a log with it? Yes or no? So, since they're both log base 2's, the arguments should be equal. X equals 12. Then you got to check that. All you're looking is when you substitute it back in, do you get a positive number back? Yes. So that checks, and 12 is our solution. Cool? Does every term have a log with it in this guy? So remember, since the entire argument is in parentheses, right, that's just part, this is one whole term right here. You with me on that? Does every term have a log with it? Yes. So the arguments must be equal to each other. Rock on. And now we get into frowny land. Quadratic equation. Get it equal to 0. So I'll subtract 3x from both sides. And let's see if we can factor him. Since a is 1, this is easily factorable. If I can find two numbers that multiply together to be -4 and add together to be -3. What do you think about those combo of numbers right there? So this is really x plus 1 times x minus 4 equals 0, to where x equals -1 or +4. You feel good with my algebra? Let's check. If I put -1 in right here, -1 squared is 1. Take away 4, what do you get? Negative. Peace out, Girl Scout. That's an extraneous answer. He does not satisfy. If you put 4 in, you get 16 minus 4, which is 12. Cool. If you put 4 in here, you get 3 times 4, which is 12. He checked. The solutions are just 4. -1 is an extraneous answer because it made the argument come out to be negative or 0, one of those two things. This guy, same thing. Log equals log. Every term has a log with it. Arguments need to be equal. Since it's quadratic, you will set it equal to 0 and factor him, if possible. If it's not possible, then you do the quadratic formula. A lot of people assume that you automatically throw out the negative one of these answers. That doesn't matter. It means when you substitute it back in, will the argument come out negative? I would choose to substitute into this one second. This is a much easier argument to deal with. You put -3 in right there, would you get a -6? So no dice for you. If you put 5 in here, you would get a +10. So far so good. You must check it then in the other one. 25 minus 15, still 10. So you check. If it checks in one, you better check it in the other one also, just to make sure. Cool? It is possible to get no solutions on these also, if they both are extraneous. Cool. Every term has a log in it, but we got a problem over here. We got more than one log. We use our rules of logarithms to condense that down to one log. So this is really log base 7 of x squared. You'll see what I did there. Yes. Then what would I do with these two arguments right here if that's an addition problem? It's going to be log base 7 of, multiply 27 times 3, which is that 729? No, 81, my bad. Of 81. Y'all down with that? So what I did was take this blue thing, and you got to condense it down to one log. If every term has a log with it, that's good news. Your idea then is to get it to log equals log, right? Condense it down, one log on one side, one log on the other. Now we have an easy scenario. Since they're both log base 7s, the arguments must equal. And don't forget, when you square root, you get 9 or -9 in that situation. Y'all cool with that? Then the real tricky part that even us math teachers have to go back and correct each other all the time is where do you substitute these back into? If you substitute in this blue thing, they'd both work. But it wasn't the blue thing that was given to us. It was this original problem. Will this satisfy right there? People are like, but it's getting squared. If you got that 2 in front of it, doesn't it really mean it's getting squared? And it's interesting, you know, you got an argument there. But the way it was originally written, it wasn't getting squared. You were taking 2 times that guy. So always substitute back into the original and realize that -9 is extraneous, +9 is Q. Yep, 6. Get that one done. They both had a log with them, So I dropped the logs and I made the arguments equal to each other, got it equal to 0, while also keeping the a value 1, so it's easily factorable. Factored it, got these two solutions. Let's see if they work or not. If I put negative 4 in there, I get a positive 44 plus 2, which is 46. I put negative 4 in here, I get 16 plus 30, which is 46, so check. 77 plus 2, 79. 49 plus 30, 79. Checks. Even though those answers were negative, by substituting back in, they both worked. Yeah. That's not what I need. Now, this is where we had the hardest time back in Algebra 2. This is still an equation, and it is logarithmic. It has logs with it. But not every term has a log with it. This has a log. This guy does not have a log with it. You first want to get it down to where you got log equals number. Right? You don't want all this other expanded stuff. You got to contract it down. Rewrite it exponentially. So when you have log base 36 of x equals a number, rewrite it exponentially. So who's the base? Who's the exponent? Is it x or is it 3 halves? You know x is the argument, right? So 3 halves is the exponent, and that will equal the argument. Now, logs are gone. Cool? Power over root. Yes, you can punch that stuff in your calculator. You know, you can punch 36 to the 3 halves power and it'll give you an answer, but means you want to do the second root. What's the second root of 36? 6. Then raise it to the third power. 6 cubed is 216. Equals x. So one more time, it's power over root. Like I said, you can punch 36 to the 3 halves power in your calculator. It'll give you an answer, right? But just to realize what to do when things get nastier, this is a root. Take the root first. So the square root of 36 is 6. Then you take that result to this power and get 216. Check him. Does he work? Does he work? Positive number, so it checks. 216. Again, logs, not in every term. You got log equals number. Rewrite exponentially. Who's the base? X to the 3 halves power equals 27. Correct? How do you solve for x? Well, you get rid of this power. How do you get rid of that power? You would raise both sides to the reciprocal power. Since that's to the 3 halves power, I will raise both sides to the 2/3 power. Because when you do power to a power, you multiply those together, and they turn out to be 1. Then you need the cube root of 27, which is 3 to the second power, 9. No need to check. The base can be a negative number, right? This is not an argument right here. This is a base. That can be negative. The only thing that you're checking back in these things is this number must be positive. Being as how he's not a variable, your answer better work, right? So 9. Yep. I got a bunch of stuff with logs in it. He's got a log. He's got a log. No log right there. So I need to condense it together first, if possible. Since I'm adding these logs together, what should I really do with these arguments right here? Multiply. I'm going to go ahead and do that in my head. Wouldn't you take x times this parentheses, and you'd use distribution to do that? Like what I'm saying is you'd really have this, and then the next move you'd have to do is distribute that through. So you got x squared minus 9x, right? And that still equals 2. All I did was take this green box of information and condense it down into one log. Awesome. And you should put that in parentheses to realize that all of this is log base 6 of that whole argument. Now, what's my move? I'd like you to get to learn to say it. You should rewrite it exponentially. So what's my move? Rewrite this exponentially. How? 6 squared equals x squared minus 9x, right? You rewrite it exponentially. Isn't this really 36 right here? So he's also got to subtract over to the other side so I can get him equal to 0 to solve this quadratic equation. So I kind of do a lot of stuff at one time, right? Two things at one time. Now factor that bad boy. Two numbers that multiply together to be negative 36. Add together to be negative 9. I'll let you find those two numbers. Which one of these guys has to be negative? The 12. So x a plus a shui times a x a minus a 12. X equals negative 3 or positive 12. And again, you've got to go back and substitute them into the original to see if there's any extraneous answers. Pretty obvious when you've just got an argument right here of x that this one's no-go. Right? You can't have a negative argument or a 0 argument either. 12 works. Put 12 in there, you get 3. That's good because it's positive, and there's your question right there. It's like, will these be the same? They are not the same because they're on the same side of the equal sign. It's not an equation. It's not like log base x equals log base, log base 6 of x equals log base 6 of x minus 9. This one's a 12. This is a 3. They don't have to be the same thing because if you had it together, log base 6 of 12 plus log base 6 of 3, it's really log base 6 of 36 because you got to multiply those numbers together and see if that equals 2. 6 squared equal 36, yes or no? Moral of my story, substitute the numbers back in. See if they are positive is all you have to do. Cool? Rocking and rolling with that? Next guy. You got a log, and no log. It means you still got to condense it down regardless of what the scenario is. You got to condense it to log equals something. So this again would be multiplication. So that's log base 8 of 2 times 4x squared, which is 8x squared, right? And that'll equal 1. I'm good with that? Now that not every term has a log with it, what's my move? Rewrite exponentially to look like 8 to the first equals 8x squared. Cool. Even though that's a quadratic equation, there are no x to the first in this, so your goal is to get x squared all by itself. Wouldn't you divide both sides by 8 and get x squared equals 1? Right? And then what does x equal? Plus or minus 1. 1 or negative 1. I don't like to put plus or minus because sometimes I have to throw out extraneous answers, so the plus or minus doesn't let me see the two separate answers. Could x be 1? Put them in here. Yes, it comes out positive. Could x be negative 1? Yes, it'll still give you a positive argument. What are we concerned about? Nice. Condense them down, baby. Condense them down. Log base 10 of, what should I do with these bad boys? Should I multiply them or should I divide them? Divide. So it's going to be, who's in the numerator, y or 2 minus y? Y is upstairs, 2 minus y is downstairs, and that equals 0. All I did was use my logarithmic rules that says when you're subtracting logs, you really can divide the arguments. Cool? Now it's log of something equals a number. Rewrite exponentially. 10 to the 0th equals y over 2 minus y. And then I'll just lightly cross him out. 10 to the 0th power is how much? Is 1. Cool? And now to solve, I'd like to get him out of the basement. How can I get rid of divide by 2 minus y? Multiply this side by 2 minus y. You're taking it times 1. Don't you really get 2 minus y equals y then? With me on that move? Add y to both sides. And y equals 1, baby. Check to see if that's an extraneous answer. 1 works here. 1 works here. You don't have to get the same thing. Well, in this case you will, because wouldn't log base 10 of 1 minus log base 10 of 1 turn out to be nothing, because they're equal to 0. But they just have to come out positive, and that did come out positive, so he checks. Last one of these. Talk yourself through it. What do I got here? Why wouldn't I do a rewrite exponentially on this situation? Logs in every term, right? So 3 minus x equals 5x minus 15. And then add x, 3 equals 6x minus 15. Is that right? Add 15 to both sides. 18 equals 6x. Yes? X equals 3. Check in. What's 3 minus 3? 0. Good or bad? That's bad. No solution. And I forgot to put the next few problems on your worksheet. So we're not quite done, even though your worksheet is over with. Why don't you please write these two problems down on your paper real quick. So you can see this is an equation, but it is not a logarithmic equation. And where's x? He's up in the exponents. What we did on the first set of problems, though, is we tried to rewrite them. If this is base 3, I'd love to rewrite that guy as base 3. But 15 is not a power of 3, correct? So there's only one way to get him to come down to Chinatown, is when there's no logs at all and you can't rewrite exponentially, you log both sides. So I will say the log of 3 to the x equals the log of 15. You log both sides. Why is that cool for us? Because I'm just doing the first one the long way. When you have log of 3 to the x, what can you really do with this guy right here? He comes down in front. So this is actually x log of 3 equals log of 15. Right? And now all I want to do is get x all by itself. Isn't there a times log of 3 hanging out with him? So what would you do? Divide. X equals log of 15 divided by log of 3. You do not get to reduce those. You can't say, is that really like log of 5? Because the 15 over 3 reduces to 5 over 1. It doesn't work that way, If they want exact answers, boom, you're done right there. That's the exact answer. If they want approximate answers, you punch that in your calculator. You would say the log of 15, close your parenthesis, divided by the log, hit the log button, log of 3, and hit equals, and you'd round how they tell you to round. Do what My Math Lab tells you to do if they say give exact answers or give approximate answers to the nearest thousandth, 10,000th, 100th, whatever they say. Okay? So next guy, 2 to the x equals 5. It is not logarithmic at all, and I cannot rewrite them with the same base because 5 is not a power of 2. Cool? So I will log both sides, and when I log both sides, this exponent comes down in front. So you really have x log of 2 equals log of 5. With me on what I did. Then x equals log of 5 over log of 2. Do you understand that concept? Well, let's see what happens now. 15, I'll give you a chance to write these down real quick. You'll want to write these down. What's the problem here? No logs, base 3, that can't be rewritten as base 3. So it comes down, but the whole exponent comes down, baby. Log both sides, the whole exponent comes down. Rock and roll. Next move. Distribute at log base 3 to both one of those guys. So this is x log of 3 plus log of 3 equals log of 8. With me on that? Next move, move him over. What would you do to move him over? Subtract, so x log of 3 equals log base 8 minus log of 3. Cool. Then what would you do? Divide every term by log of 3. So x equals log base 8 minus log base 3 all over log of 3. That's one way to do it. That's the way our book wanted it done. That's why I looked that up real quick, because that's the way our book wanted it done. I wouldn't do it that way. I would have done this. Well, hold on. Let me keep that there. Let me just start it over real quick and show you how these are the equivalent things. So what I had was x plus 1 log of 3 equals log of 8. You with me? That's this guy right here. So what I do is I do this. Right? And those are gone. X plus 1 equals log of 8 over log of 3. What would you do to get x by itself then? So x equals log of 8 over log of 3 minus 1. Are these two things the same? What do you think? Well, if I would have done this, instead of all over, divide every term by log of 3, what do you think that turns out to be right there? That's 1, right? Negative 1. Cool? So it doesn't matter which way you roll with it. Number 16, there are going to be a few of these also. See how x is in the exponent. There's no logs whatsoever. Your job, first, get that all by himself. What would be our first move? Add 11. So 4e to the x equals 28. Right? Then get this all by himself. What would you do? Divide by 4. Cool? Then what would you do? Most people say log both sides. You want a natural log because the base is e. So if I natural log both sides, you'd get x comes in front, natural log of e, natural log of 7. Right? This is a long way to do this one also. Who knows what that is, really, right there? Isn't this base e right here, and that's e? So what's natural log of e? It's really 1. So you have x equals natural log of 7. What you could have done right away is realize you're at base e, just rewrite it logarithmically. Isn't this, if you rewrite it logarithmically, say the natural log of base e of 7 equals x. This is your argument, this is your exponent, this is your base right here. Same concept either which way. Cool? So, plenty of time to work on my math lab.